Question 1. Digital television in New Zealand can be accessed using a satellite dish pointed at a satellite in space. The satellite used to transmit signals appears to stay still above the equator. The satellite, with a mass of 300 kgs, is actually traveling around the Earth in a geostationary orbit at a radius of 4.22 times 10 to the 7 meters from the center of the Earth. Name the force that is keeping the satellite in this circular orbit, and state the direction in which the force is acting. Okay, so the force that is keeping the satellite in orbit is actually the weight force. Now, a common thing that people get wrong is they say that the force that is keeping the satellite in orbit is actually the centripetal force, which this is not the case. If we remember, the centripetal force is not a real force in and of itself, it is provided by another force, and in this case the centripetal force is provided by the weight force. So what's actually happening is if we have Earth right here, and we have a satellite that is traveling around in orbit, there is a weight force that is attracting it to the Earth. As for the direction of this weight force, it always acts towards the center of the Earth. So even if the satellite is over here, the weight force is now going to act in this direction. So notice how the weight force changes direction in these two positions. And if it's over here, the weight force is going to act this way. So it always acts towards the center of the Earth. Calculate the force acting on the satellite. Okay, so the force acting on the satellite is our Fg, and we know our Fg is equal to the gravitational constant times big mass, little mass, all over r squared. Now remember, in this case, the big mass is the mass of Earth, right? And the little mass is the mass of the satellite, right? Now we know that the mass of the satellite is 300 kgs. Right? And the mass of the Earth is given to us up here, 5.97 times 10 to the 24 kgs, right? As for our radius, remember in this equation, the radius is actually referring to the distance between the center or masses of the two objects. So in this case, we want the distance from the center or mass of Earth, so imagine this was Earth, right here, and this was our satellite. We want the distance from the center or mass of Earth to the center or mass of the satellite. And so if we look at the values that they have provided us with, we can see that this value here, 4.22 times 10 to the 7, is the distance from the center of the Earth. So that is the distance that we want. Now you notice we're not given the radius of the satellite, so the distance from the external side of the satellite to the middle. We're not given this because in this scenario, we can assume that the satellite is a point source. And what that means is that we don't assume the satellite has an outer edge, we just assume it as a little dot. The reason for that is because the size of the Earth is so much bigger than that tiny little satellite that extra little distance doesn't really affect the equation that much. And so we can assume it as negligible. And so in our scenario, we will have a point source for our satellite, and we'll have the Earth right here. And that distance is our 4.22 times 10 to the 7 meters. Right there. So now that we have all our values, because g is just a constant, we can plug it in to find our Fg. So we know that Fg is equal to our gravitational constant, which is 6.67 times 10 to the negative 11, times our big mass, which is 5.97 times 10 to the 24. Remember, that's just the mass of Earth, times our little mass, which is the mass of the satellite, which is 300 kgs, almost running out of space there. And that's all over our r squared, which is 4.22 times 10 to the 7. And that is squared. And this gives us a value of Fg as 67.1 newtons. There we go. Show that the speed of the satellite is 3.07 times 10 to the 3 meters per second. So as discussed previously, we know our Fc is equal to our Fg. And so our Fc, as we know, is mv squared over r. And our Fg, which we just used in the previous question, is g big mass, little mass, all over r squared. Now, as you can see, we have our little mass on both sides, which is just the mass of the satellite. And so because of that, we can divide by m on both sides, and what happens is that these masses just cancel. And therefore, that simplifies our equation to v squared over r is equal to g big mass all over r squared. Now, if we rearrange by moving this r up here, we get v squared is equal to g big mass r over r squared. Now this r will cancel out with this power, and we get v squared is equal to g m all over r. And because we just want r by itself without that square, we can square root both sides, and we get v is equal to square root gm all over r. Okay, so now that we have our equation, we can look at our variables. We have our gravitational constant because it's just a constant, we always have it. We have our big mass, which is just the mass of the Earth, and we also have our radius. So we have all our values, so we can just plug the numbers in, and we get v is equal to the square root of g, which is 6.67 times 10 to the negative 11, times our big mass, which is 5.97 times 10 to the 24, all over our radius, which is 4.22 times 10 to the 7. And that gives us a velocity of 3,071 meters per second, which is indeed the same thing as saying 3.07 times 10 to the 3 meters per second. And as you can see, that is exactly what we're trying to find. Kepler's law states for any orbiting object, t squared is directly proportional to r cubed, where r is the radius of the orbit and t is the time period of the orbit. NASA uses a robotic spacecraft to map the moon. This spacecraft orbits the moon at an average height of 50 times 10 to the 3 meters, with a period of 6.78 times 10 to the 3 seconds. The moon has a radius of 1.74 times 10 to the 6 meters. Use Kepler's law to estimate the mass of the moon. And in our answer, we should derive Kepler's law, and also use Kepler's law to determine the mass of the moon. So if you haven't seen it already, I have a full video on how to derive Kepler's law. Kepler's law is basically going off the same principle that we used in the previous question, where our Fg is equal to our Fc, and so therefore our G big mass, little mass, all over r squared is equal to mv squared over r. Again, we can cancel out our masses, and we get Gm all over r squared is equal to v squared all over r. And again, as we did in our previous question, we can cancel out the powers of the radius, and we get Gm all over r is equal to v squared. Okay, so we get to this point, and we're like, where is the t going to come in? And we only have one r, not r cubed. So that's when we have to use our knowledge of circular motion. We know that velocity is equal to distance over time. And as this satellite is orbiting around the moon in a path as so, we can say that the distance that the spacecraft travels is the circumference of the orbit, correct? And so the circumference of the orbit is just the circumference of a circle. And so we know the circumference of a circle is 2 pi r. And so 2 pi r is equal to our distance. And we also know the time taken for a satellite or a spacecraft to complete one orbit is defined as 1 period. And so our time is just 1 period. And so we can redraw that velocity equation as 2 pi r over t. And so now we can plug that into this equation, and we get Gm all over r is equal to 2 pi r over t squared. And now expanding that squared term, we get 4 pi squared r squared all over t squared. And now doing some simple rearranging, we get Gm t squared is equal to 4 pi squared r cubed. And as you can see, t squared is directly proportional to r cubed, right here. And that is what we need to derive. Now, this question isn't specifically asking us to derive Kepler's law. Even though it says right here in the question, that's just wanting us to show our working. We actually need to use this law to find the mass of the moon. And so as we know from our equation, this big mass is equal to the mass of the moon, right? And so essentially we just need to rearrange for our big mass. And so we can do that by dividing by t squared on both sides. And we get m is equal to 4 pi squared r cubed all over gt squared. And so now that we have our formula, we can look at our variables and see what we have. We have 4 pi squared because 4 times pi squared, we always have that. We also always have our g, which is our gravitational constant. Our t squared is just our period squared, which we have right here. And our r, we also have, however, there's a slight caveat. This is the slight twist that I alluded to earlier in this video. We have the height that the spacecraft orbits above the moon, and we also have the radius of the moon. And so what that means is we have the spacecraft over here. Again, we can draw it as a point source, and we also have the moon. We are given the height that the spacecraft travels above the moon, which is 50 times 10 to the 3 meters, and we're also given the radius of the moon, which is 1.74 times 10 to the 6. Not quite drawn to scale, but you get the idea. And so, as I said previously, this r is actually the distance from the center of mass of the satellite to the center of mass of the moon. And so our r is equal to 50 times 10 to the 3 plus 1.74 times 10 to the 6. And that gives us a radius of 1.79 times 10 to the 6 meters. And so now that we have all our values, we can just plug them in, and we get the mass is equal to 4 pi squared r cubed, which is 1.79 times 10 to the 6, and that's all cubed, all over our g, which is again 6.67 times 10 to the negative 11, all over our period, which is 6.78 times 10 to the 3, and that's all squared, and that gives us a mass of 7.38 times 10 to the 22 kgs. There we go. Okay, moving on to question 2. Okay, so this description is sci-fi. NCEA try to mix in a movie into the question. There was a lot of controversy on this because they're putting science fiction in a physics paper, but essentially the idea is that there is a elevator that can go straight through the Earth, and the elevator is being accelerated by gravity because there's no friction. And so if there is no friction, the elevator is going to start at the top, accelerate due to gravity, and once it gets to the midpoint, we're going to be on this side now, right? And because once we're on this side, gravity is going to act in this direction, and so that's going to slow us down. And so that's kind of the idea that they're trying to get at. Again, makes no sense because you can't go through the center of the Earth, and they try to explain that in the question as well. They try to be like, oh, you're going to be protected, but still, it doesn't really make any sense. But moving on. Anyways, one of the passengers on the elevator stands on bathroom scales at the start of the journey. Describe why the bathroom scales read 0. Okay, so in order to understand this problem, we need to understand what is happening when you're on regular bathroom scales on a non-falling platform, just in your bathroom. So we have you right here, and you're on some bathroom scales, like that, okay? Now, when you're on these bathroom scales, you have a weight force acting downwards. Now, I don't know about you, but when I step on bathroom scales, I don't fall straight to the ground. I kind of stand there in place. And so what that means is there has to be a force acting upwards that is equal to my weight force. Because if there was no force acting upwards, the weight force will just pull me straight through the Earth, which doesn't happen, hopefully. And so we call this the normal force. And so this normal force is provided by the scales and also the floor. And the reason why it can provide this force is because there is contact between you and the scales. However, when we're in this elevator, this mysterious elevator, we're in the elevator right here. Again, we're standing on some bathroom scales. The elevator is going to be accelerating downwards at 9.8 meters per second, right? Because it accelerates at the same rate of gravity. And so if the elevator is accelerating downwards at 9.81 meters per second, you are also going to be accelerating at 9.81 meters per second because you're in the elevator. And what that also means is that the scales is also going to be accelerating downwards at 9.81 meters per second. So what that means is there is no contact force between you and the elevator. You and the elevator are going to be moving down at the exact same rate. And so essentially, none of your weight is on the scale itself. You're essentially touching the scales, but you're moving at the exact same rate as the elevator. And so even though you're touching the scales, there is no contact force between you and the scales. And so that's a very long and convoluted way of saying that you and the bathroom scales are accelerating downwards at the same rate, and therefore there's no contact forces between you and the bathroom scales. Calculate the maximum acceleration of the elevator. Okay, so there are two ways you can look at this question. One way is to go straight from the description given. It says that this elevator is going to be harnessing the gravity of the planet, and we know that the acceleration due to gravity on Earth is equal to 9.81 meters per second, right? And so therefore, as the elevator is harnessing gravity, the maximum acceleration that it can hit is the acceleration due to gravity. And so therefore, you can say that the maximum acceleration is going to be 9.81 meters per second. And that is a totally valid answer. Now, another way we can find the maximum acceleration of the elevator is to calculate it. So the way we will calculate it is if we look at our given values, we can see that the acceleration is this value right here. Now, this value is not something we've seen before, but if we think about it, we can break it down and it becomes kind of obvious. So this value is our acceleration is equal to negative 1.54 times 10 to the negative 6 y, where y is the distance from the midpoint. Now, the midpoint is referring to the midpoint of the Earth, so essentially just the radius of the Earth, which we are also given up here. So the radius of the Earth is 6.38 times 10 to the 6 meters. Okay, so moving back to this equation, we've never really seen it in this form, but this equation is on your formula sheet, and it's in the form A is equal to negative omega squared y. And now it becomes kind of apparent that omega squared is equal to 1.54 times 10 to the negative 6. And so now we can just plug in our numbers. We can get the acceleration is equal to negative 1.54 times 10 to the negative 6 times y, which again is the distance to the midpoint, which is just our radius, 6.38 times 10 to the 6, and that gives us an acceleration of 9.82 meters per second, and that is going to be a negative value, again because acceleration is downwards. However, you do not need that negative value there. And so as you can see, both methods give you basically the same answer. However, one was just straight from intuition and the other was calculation. Both are correct, but I would prefer this method right here, just purely because it's faster. Calculate the maximum linear velocity of the satellite. Okay, so as stated previously in that previous question, omega squared is equal to 1.54 times 10 to the negative 6 radians per second. Now we know our Vmax is equal to A omega, again A being the amplitude, which in this case is just the radius of the Earth. And so therefore, Vmax is equal to 6.38 times 10 to the 6 multiplied by the square root of 1.54 times 10 to the negative 6. Again, we square root because this is squared and we just want the regular version, not the squared version. So we square root. And so Vmax is equal to 7917 meters per second. There we go. Explain how the equation given shows that the elevator is undergoing simple harmonic motion. Okay, so the equation that they're talking about is our A is equal to negative 1.54 times 10 to the negative 6y, right? Okay, so if we understand our situation, we can see that we have our Earth right here and we have our elevator at the top. The elevator is going to go downwards, right? This is because the force of gravity is going to act towards the center. And as it reaches the midpoint, the elevator is going to be like right here. Its motion is going to be directly downwards. However, the force is going to be upwards, right? And so we can see that this is actually very similar to a pendulum, right? If we have a pendulum, this is the equilibrium position. We can imagine that when the bob is at this position right here, there is going to be a force accelerating it towards the center. However, once it moves past that center point and is now over here, we can imagine again the motion is going to continue this direction. However, there is going to be a force pulling it in this direction, thus causing it to slow down. And so that's a very similar thing that's happening here. We have a force that is pulling it down. However, once it goes past the midpoint, aka the equilibrium position, there's a force causing it to go back up, and therefore the elevator slows down before it reaches the end. And so put into words, the acceleration or restoring force, again, F is equal to ma, and the mass of the elevator does not change, and so basically F is directly proportional to A. And so you can substitute force or acceleration in this context. And so the acceleration is in opposite direction to the displacement, hence the negative sign right here. And the acceleration always acts towards the equilibrium position. In this case, the equilibrium position is the midpoint. And another point is that the acceleration is directly proportional to the displacement, because y is the radius of the Earth, which, as you can see, is the displacement of our simple harmonic motion. Calculate the time the journey from the North Pole to the South Pole would take. Okay, so as we discussed in the previous question, this situation is basically the same thing as simple harmonic motion. And so therefore we can say it has a frequency, correct? And we know the frequency is equal to 1 over t. We also know that our omega is equal to 2 pi f. And so therefore our omega over 2 pi is equal to our f. And so therefore omega all over 2 pi is equal to 1 over t. Now we can take the inverse of both sides and we can say that 2 pi all over omega is equal to our period. Now in previous questions we know that our omega squared is equal to 1.54 times 10 to the 6, and therefore our omega is equal to the square root of 1.54 times 10 to the 6. And therefore 2 pi all over our square root of 1.54 times 10 to the negative 6 is equal to our period, which gives us roughly 5,000 seconds, which is equal to 84 minutes. There we go. Cats have the ability to orientate themselves in a fall, allowing them to avoid many injuries even when dropped upside down. Cats can even do this without tails, and they don't need to be rotating first in order for this to happen. The sequence of events for a typical 3 kg cat: the cat determines which way is up by rotating its head. The cat exerts an internal force to twist the front half of its body to face downwards. The cat then exerts an internal force to twist the back half of its body to face downwards as well. And the cat then lands safely. The cat can be modeled by a pair of equal mass cylinders, the front and the back half of the cat, linked at the center of mass of the cat. The moment of inertia is directly proportional to mr squared. Describe the motion of the center of mass of the cat during its fall, and explain why the linear momentum of the cat is increasing. Okay, so if we have the cat modeled as 2 rectangular cylinder things right here, let's make them more even, like so. The center of mass is going to be somewhere over here. And we know that as the cat falls, there is going to be a single force, which is the weight force, acting downwards. And therefore, the motion of the center of mass is just going to move directly down and accelerating due to the weight force. Now, the linear momentum will increase because there is an external force acting on it. We know that momentum does not increase when there is no external forces. However, in this case, there is an external force, the weight force. And so the linear momentum will increase because this weight force is acting on it. And therefore, the linear velocity will increase. In the vertical direction, that is. Considering only the first half of the fall, with the cat's legs tucked in, the front half of the cat can be modeled by a cylinder of radius 0.06 meters. During the first part of the fall, the cat uses its muscles to twist the front of its legs quickly to reach an angular velocity of 1.2 radians per second. If the angular momentum of the front half of the cat is 3.24 times 10 to the negative 3, calculate the rotational inertia of the front half of the cat. So we know our angular momentum is equal to I omega, and therefore we can simply rearrange this for I is equal to L over omega. We are given our angular momentum up here, 3.24 times 10 to the negative 3, and we are also given our angular velocity, 1.2. And this gives us a rotational inertia of 2.7 times 10 to the negative 3 kg meters squared. There we go. The cat is able to twist the front half of its body even though the total angular momentum must remain 0. Explain why the total angular momentum of the cat must remain 0, and explain what must happen to the rear of the cat's body. Okay, so when the cat is in the air, there is no external force acting on its center of mass. Right, we know this because in the description, we can see that the cat only exerts internal forces, and therefore there is no external forces. And so by this, the angular momentum of the cat's center of mass cannot change. However, if we model our cat again, we know that the front half, this half right here, has increased its angular momentum. It has rotated. You can imagine this is rotating into the page like that, right? It has rotated in that direction. And therefore, in order for the angular momentum to remain 0, the rear has to rotate by the same amount in the opposite direction. And so the back half is moving out of the page, you can see, like this. And so they're going to be in opposite directions. And so essentially you can write a beautiful answer with that theory. During the first half of its fall, the cat stretches out its rear legs. The rear half of the cat can be modeled as a cylinder of radius 0.12 meters. Explain how the cat can rotate the front and rear of its body at different speeds. In your answer, you should calculate the angular momentum of the rear half of the cat, explain why there is a difference in rotational speed between the front and rear halves of the cat, and calculate the angular velocity of the rear half of the cat. So as discussed in the previous question, angular momentum must equal 0, and so the angular momentum of the front plus the angular momentum of the rear must equal 0. And so rearranging this, we can say that the angular momentum of the front is equal to negative angular momentum of the rear. And so we know that the angular momentum of the front is 3.24 times 10 to the negative 3. And therefore, the angular momentum of the rear is equal to negative 3.24 times 10 to the 3. Okay, so now moving on to explaining why there's a difference in rotational speed between the front and rear halves. And this has everything to do with the fact that when the cat falls, it pulls in its front legs and extends out its rear legs. And so if we just look at the front part of the cat, this is the front part of the cat, and we can pull in our legs. These are our legs, these two sticks, okay? We can imagine if we pull in our arms, our effective radius is going to decrease. And so we know that I is equal to mr squared, or in this case, it's not actually equal to, it's directly proportional to. Right? What that means is there is a constant in front that we don't know of, but that's not needed for this question. And so if our radius decreases, that means our rotational inertia will decrease as well. So the effective radius is decreasing because more of our mass is closer to the axis of rotation, aka the center of mass. And so therefore, as angular momentum is equal to I omega, if I decreases, therefore as angular momentum is conserved, our angular velocity must increase. Now the opposite is true for the rear of the cat. If we draw the rear of the cat, we've just dissected the cat in half. The rear legs spread out like this. Those are our rear legs. And again, as I is directly proportional to mr squared, as we have stretched out our legs, our mass is further distributed from the axis of rotation, and therefore our effective radius has increased. And so therefore, as our effective radius is increased, our rotational inertia must also increase as they're directly proportional to each other. And same thing, as angular momentum is equal to I omega, as angular momentum does not change, it is conserved. If our I increases, therefore our angular velocity must decrease. And that is why the rotational speed of the front half of the cat is greater than the rotational speed of the rear of the cat. Okay, so now we need to calculate the angular velocity of the rear of the cat. So we know that our I is directly proportional to mr squared, and as I said previously, it is directly proportional because in reality there is going to be a constant, mr squared, where our k is our constant. This constant is usually something like 2 over 3 or like 2 over 5 or something. That's not necessarily important in this case. Now, if we look at our situation where we have the front half of the cat and the rear half of the cat, like that, we can assume that the mass is evenly distributed in the cat. What that means is that the front half of the cat has the same mass as the rear half of the cat. And so what we can basically say is that this mass does not matter in this equation. If we're just talking about rotational inertia, if the mass is the same on both sides, they can cancel each other out. And so it's not necessary in our calculation. Same thing with this constant. This constant is going to be the same on both sides, and so we can just get rid of that as well. And so what we're left with is rotational inertia is directly proportional to r squared. Now what we also know is that angular momentum is equal to I omega, and as we know that the angular momentum of the front is equal to the angular momentum of the rear, right? And so because of this, we can rewrite this equation as the rotational inertia of the front times the angular velocity of the front is equal to the rotational inertia of the rear times the angular velocity of the rear. Now, through some rearranging, we can say that the rotational inertia of the front divided by the rotational inertia of the rear is equal to the angular velocity of the rear divided by the angular velocity of the front. Now, this is where this equation comes quite handy. Because rotational inertia is directly proportional to r squared, we can sub in r squared for our rotational inertias. And so we get the radius squared of the front all over the radius squared of the rear is equal to the angular velocity of the rear all over the angular velocity of the front. Now, what we're trying to find is the angular velocity of the rear, and so we can rearrange by timesing both sides by the angular velocity of the front, and we get r squared f times by omega f all over r squared r is equal to our angular velocity of the rear. Now, we know from previous questions that the angular velocity of the front is equal to 1.2. We also know from previous questions that the radius of the front is equal to 0.06. And we also know that the radius of the rear is equal to 0.120. And so now plugging in our numbers, we get the radius of the front is equal to 0.06 squared times 1.20 all over 0.120 squared. And that gives us an angular velocity of the rear as 0.3 radians per second. There we go. And with that, it looks like we're done. Sweet as. Again, if you like these videos and you would like extra help from me directly, I have a program linked in the description where you can gain access to my help. So again, if that sounds of any interest to you, you can go check that out. Sweet as. See you next time.